Hi, in this episode we're going to take a look at coordinate transformation. Coordinate transformation is very important in robotic analysis. We will discuss the transformation matrix as well as the vector transformation from one coordinate to another coordinate using the transformation matrix. The motivation for that is, as you see here, a robot can have several coordinate systems, such as a fixed coordinate system to the base of the robot. We call that inertial frame, as well as moving coordinate system, such as the one which is attached to the base of the robot, the one which rotates with respect to the frame. And we may have another several coordinate systems, such as the one which is connected to the link of one of these elements of the robots. So we may have inertial, base, arm, end of arm tool. All of these coordinates may be associated with the robot. Now, the specification of some of the robot parameters, such as arm length or arm velocity, sometimes are conveniently done within a rotating coordinate system, or what we call body fix, such that the arm of this link will be conveniently measured in this coordinate system rather than any other coordinate system, or the arm velocity with respect to the base will be measured conveniently with respect to a rotating coordinate system. And at the same time, physical phenomena such as Newton's second law, F equals ma, have to be expressed in inertial coordinate system. And for that reason, we have to be able to transfer vectors from one coordinate system anywhere in the robot system to the inertial frame. Now, to take a look at this, what we'll see here is that we have an inertial frame with another rotating frame which is positioned at angle theta with respect to the inertial frame. Now, we have a vector r representing the position of point A, represented in coordinate system 0. It has component rx0 and ry0. And what we like to do is find out the components of the same vector along axis x1 and y1, and we call them rx1 and ry1. So we have r0 with its component rx0, ry0, and there is no z component, therefore this one is 0. And we have r1 represented by its component, rx1, ry1, and 0. And the question is, what will be, knowing r1 and the x1 coordinate system, what will be the components of r0 along the x0 component, x and y, x0 and y0 coordinate system. So to do that, what we do is we take the r1 vector and multiply this by the transformation matrix from coordinate system 1 to coordinate system 0, and that multiplication gives us the coordinates of vector r along the 0 coordinate system. Now, the components of the transformation matrix 1 to 0 is cosine theta minus sine theta and cosine theta, with 0, 0, and 1 over here for the third row. We'll see in a minute why. And the multiplication of the matrix, transformation matrix, times the component of vector r in coordinate system 1 will result the components of vector r in coordinate system 0. The result of this multiplication is the rx0 equals cosine theta times rx1 minus sine theta times ry1 plus 0 times 0, and this is what's written here, and the component ry0 equals to sine theta times rx1, what we see here, plus cosine theta times ry1, what we see here, and the z, which is actually equal to 0, equals to 0 times rx1 plus 0 times ry1 plus 1 times 0, all of that equals to 0. So this is the expression and the result of the transformation of vector r represented in x1 coordinate system to vector r represented in the 0 coordinate system. It is also convenient to see this little sketch in order to figure out the signs. And as we see here, vector rx0, okay, equals to rx1, which is this line all over here, times the cosine theta, and that will be the projection over here, so it will be the distance from this point all the way here, and then we have to subtract from it a little portion over here, which is exactly ry1 times the sine of theta, with this element over here, and this is what we have in here. At the same time, ry0, which is this length from here to here, equals to rx1 times sine theta, this distance here, rx1 sine theta, plus ry1 times cosine theta, which is this component here. So the two together will give us ry0. So sometimes it's convenient to look at the sketch and figure out which are the sign. It's always cosine on the diagonal, 1 along the axis which is the axis of rotation, z in this case, and it is minus sine the angle and plus sine the angle depending on the direction of rotation, and you can use this sketch to figure out whether the sine has a minus sign here or is it a minus sign here. So this concludes the presentation of coordinate transformation, which we'll be using in upcoming discussion. Thank you.